Hello everyone, welcome back to Engineering Escapades. Today I'd like to go through some more transistor basics, and what I'm going to talk about today are some basic logic gates. The two most basic logic gates that we have that use two transistors each. So let's just have a look at what they actually do before anything else. So the output of this one is on the emitter of the transistor, or the leftmost transistor, let's just say in this case. You'll see later on that it doesn't really matter which emitter we put it on, but let's just say the output is over here right now. So, when none of the switches are pressed, so let's call this switch A and this switch B. Let's see, just scoot this over here so we have plenty of space. So let's see. Then the output, and let's call that Q. So 0, 0, and the output Q is off. So let's just set up all the other cases of the switches. So A could be on and B could be off, and they both could be on. So let's just go through these. So we'll see that when I press B, we can see Q is on. And when I press just A, we can see that Q is also on. And when I press both of them, it's still on. And this is what is called an OR gate. So let's just do this. And you can see why it's called an OR gate, because if A is on or B is on, then the output is on. And that's where the OR logic comes from. You'll see that the one in the center here is the same as last time, though. I forgot to mention that. Let's have a look at the other one over here. And the output of this one is after this resistor right here. And immediately you'll see that this acts differently. And if we set up one of these truth tables, they're called, we'll see how it's different. So we can immediately see that when A and B are off, Q is on. So let's just go through the rest of these and then see what this circuit has to offer. So when B is pressed, it's still on. When A is pressed, it's still on. But when both of them are pressed, Q turns off. And that's kind of weird, isn't it? So, first of all, I'd like to introduce you to another way of writing these circuits before we move on. We'll have a look at the other circuits first, but let's have a look at the center one first of all. So, as you can see, we have 5 volts here, and then the LED, then the resistor, then the transistor, and then the ground. And when the input receives no current, then the transistor is off, and current cannot flow through the LED. So we just use this to receive signals, really. But this is another way of writing a circuit, which doesn't involve batteries, so it's a lot easier, you can say. It's a lot easier to read, it's a lot less clutter. But anyway, let's now have a look at these two circuits right here. So, we will have a look at the OR gate first. So as you can see, the collectors of both the transistors are connected, and the emitters of both transistors are also connected. So these are connected in parallel, which means that if either of them turns on, current is allowed to flow. And if both are on, current is still allowed to flow, of course. And you can see that when one of them turns on, or both of them, the voltage potential at this node Q rises to our 5 volts and gives us a signal out. So let's just have a look at that again. You can see that when I press the switch A, output turns on. Press switch B. You'll see that when I press this switch, you can see that the current is now flowing through this wire through here, through this transistor, and then goes to Q. And since we have this resistor here, the potential here is higher than just ground, of course. The same happens for A. We can see that it flows through here and then through Q and then ground. And then if I press both of them at the same time, we can see that it's basically allowed to flow through both of them. So it's distributed. So yeah, that's not very exciting. But let's have a look at the NAND gate, because it's what this does. It is a not AND. And as you'll see, when I press a switch, current is not allowed to flow through this circuit. And when I press the other switch, current is still not allowed to flow through this circuit because this one is on and this one is off. But when I press both of them, we can see that current is allowed to flow, so the voltage potential at this node drops to 0 volts. And since we have 0 volts at the input here, then current cannot flow through this circuit over here. And that's great. But you might be thinking, well, couldn't we just make an AND gate with 2 transistors? And I'm going to show you why we can't. So let me just grab my little tools here and then just move some stuff around. Let's have this out. Let's take this, plug this in like that, and then add this resistor to flow that to ground. So what I have essentially done now is I've moved this resistor to the other side, and I've moved this Q to the other side as well. So let's have a look at how that works. And from the get-go, it might seem like it works. When I'm pressing A, the LED doesn't light up. When I'm pressing B, the LED doesn't light up. And when I'm pressing both, it does light up. But that is a lie, because when I'm pressing A, the LED does slightly light up. And you'll see this even better if I remove this resistor that was in the path of this transistor over here. So when these are kind of hard to work with. When I click A, it turns on, and that's not good. And the reason for this is because, as I told you in the last video, a transistor is activated by a current flowing from the base to the emitter. And when I'm turning this on, I'm allowing current to flow from the emitter, or from the base to the emitter. And not all of this flows through this resistor to ground. Some of it flows through this wire to the base of this transistor. And that's not very good. So how then would you actually create an AND gate? Well, some of you may have noticed that the answer is quite simple already. And it has to do with a circuit we built in the last video, which is the inverter. And with the inverter, we can build 2 other types of gates, which is the NOR gate and the AND gate. So just to give some kind of intuition of how one would do that, you'd just wire the outputs of these. Instead of going through this, you'd first go through the inverter and then to this after the inverter. So the truth tables for those would be the exact inverse of this. So the OR gate has this truth table, but the NOR gate, which it's called, it's an inverted OR gate, would look like this. And the AND gate, which is an inverted NAND gate, because the inverse of an inverse is just the original input, so the invert of a NAND gate is an AND gate, and that would look like this. and there we have our AND truth table. So that was pretty much it for this video. In my next video, I'd like to talk to you about some more complicated logic circuits built from transistors, some more logic gates. So we'll have a look at those next time. But for now, thank you for watching. Subscribe if you'd like to see more of this. Like the video if you liked it. If you didn't like it, then you can dislike it. But please tell me down in the comments what you'd like to change and also what you'd like to see in my next video. So goodbye.